Across widely separated regions of the ancient world, from the floodplains of the Nile to the high plateaus of the Andes, from the river valleys of northern India to sites scattered across the Mediterranean and beyond, stone artifacts exist that quietly but insistently challenge modern expectations about early technological capability. These objects do not merely demonstrate that ancient peoples could quarry, transport, and shape stone. That much has never been in doubt. What unsettles careful observers is the level of precision embedded in these works. Surfaces finished to near mirror smoothness, internal symmetries that deviate by only fractions of a millimeter, geometries that remain consistent across entire sites, and material outcomes achieved in stones that are among the hardest and most brittle available in nature. Granite, diorite, basalt, and andesite are not forgiving materials. They fracture unpredictably, resist abrasion, and punish imprecision. Yet again and again, the archaeological record presents objects shaped from these stones with a degree of control that appears to exceed what is conventionally attributed to pre-industrial societies. This problem of impossible precision does not arise from a single artifact or an isolated site. It emerges from patterns. In Egypt, 4th dynasty stone vessels carved from granite and diorite exhibit internal circularity and concentricity so consistent that modern engineers can measure them using geometric dimensioning and tolerancing standards. In India, the Ashokan pillars stand as single-piece sandstone columns with surface polish so uniform and reflective that even today it is difficult to replicate without industrial abrasives and mechanized rotation. In Peru and Bolivia, polygonal masonry blocks interlock with such exactitude that razor blades cannot be inserted between joints, despite the stones being irregular in form and carved from andesite, a volcanic rock notorious for its hardness and fracture behavior. These examples are not rare curiosities tucked away in museums. They are integral to state-sponsored monuments, ceremonial architecture, and infrastructural projects that required coordinated labor, planning, and standardized methods. The significance of this cannot be overstated. When precision appears repeatedly across a culture's most important constructions, it ceases to be the product of isolated genius or artistic flourish. Instead, it points towards systematic knowledge. Precision of this kind requires repeatability. Repeatability requires process. Process implies an understanding not only of form, but of material behavior, tool interaction, pressure application, sequencing, and error control. These are not accidental outcomes. They are the signatures of codified practice, even if that practice was never written down. At the heart of the mystery lies a subtle but crucial distinction. The question is not whether ancient peoples could shape stone. Hammering, pecking, grinding, and polishing are well within the reach of human ingenuity using simple tools. The deeper question is how ancient artisans achieved controlled, repeatable, high-precision results in materials that resist such control. Shaping stone crudely is one thing. Producing hundreds or thousands of stone elements that conform to consistent geometric standards across different work crews, quarries, and time spans is something else entirely. The latter requires not just effort, but understanding. Modern archaeological explanations often acknowledge the aesthetic or symbolic importance of these artifacts, while quietly sidestepping the engineering implications embedded in their physical properties. A polished surface is described as ceremonial or ritualistic. A perfectly aligned joint is attributed to patience and skill. Symmetry is praised as artistic sensibility. While none of these interpretations are necessarily wrong, they are incomplete. They tend to treat the stone as a passive canvas upon which meaning was imposed, rather than as an active medium that records the consequences of technical decisions. By focusing primarily on cultural symbolism, conventional narratives frequently underplay the fact that the material outcomes themselves demand explanation at the level of process. Stone does not lie. Unlike texts, which can exaggerate, mythologize, or omit, stone faithfully preserves the results of physical interaction. Every groove, every polished plane, every internal corner reflects a history of force, motion, and material response. When tools vanish and workshops disappear, the stone remains as the final output of a manufacturing sequence. It is, in effect, a frozen record of process. This is why the stone itself becomes the primary source of evidence when written manuals and tool catalogues are absent. The artifact is not merely an object to be admired. It is a data-rich surface awaiting interpretation. Consider surface finish alone. Producing a flat, smooth surface on hard stone requires controlled abrasion. The uniformity of that finish reveals whether pressure was applied evenly, whether motion followed consistent paths, and whether abrasive particle size was standardized. Random rubbing produces random textures. Systematic polishing produces recognizable patterns. In many ancient artifacts, these patterns are so consistent that they suggest not only deliberate technique, but also an awareness of how small variations in pressure or motion would affect the final result. This level of control implies feedback. Feedback implies measurement, even if that measurement was sensory rather than numerical. An artisan must know when a surface is flat enough, smooth enough, symmetrical enough, and must be able to reproduce that judgment reliably. Symmetry provides an even more striking example. Internal symmetry, especially in hollowed stone vessels, cannot be easily judged by eye alone. Deviations of a few tenths of a millimeter are below the threshold of human visual perception, yet such deviations are precisely what modern measurements reveal in certain ancient objects. Achieving this degree of symmetry repeatedly suggests the use of reference geometries, guides, or procedural constraints that enforce consistency throughout the carving process. Whether these constraints were mechanical, geometric, or procedural is still debated, but their existence is strongly implied by the results. Geometric control on an architectural scale raises the stakes further. At sites like Machu Picchu or Pumapunku, massive blocks carved from andesite fit together with astonishing precision across entire complexes. These blocks were not carved in isolation. They had to conform to neighboring stones, align with structural loads, and maintain consistent joint behavior. The repetition of similar angles, corner radii, and joint geometries across a site suggests shared standards. Shared standards require communication, training, and enforcement. This is not ad hoc craftsmanship. It is organized engineering. Yet conventional narratives often resist this conclusion, not because the evidence is weak, but because it conflicts with deeply ingrained assumptions about technological progression. There is a widespread belief that advanced precision requires advanced machinery, and that advanced machinery is a product of modern industrial society. When confronted with ancient precision, the default response is to attribute it to extraordinary labor investment, trial and error, or lost time, rather than lost technique. The implication is that with enough effort, any result is possible. But this overlooks the fact that effort alone does not guarantee consistency. 10,000 random attempts do not converge on a precise outcome unless guided by a controlling framework. This is where the engineering implications become unavoidable. Precision is not simply a matter of working harder. It is a matter of working smarter, of constraining variability, of understanding which parameters matter and which can be ignored. In modern manufacturing, this understanding is formalized through tolerances, process controls, and quality assurance. In ancient contexts, the same principles could exist in tacit form, embedded in practice rather than text. The absence of written equations does not imply the absence of engineering thought. Empirical knowledge, accumulated through observation and transmitted through apprenticeship, can be extraordinarily powerful. The stone artifacts themselves testify to this. They preserve traces of motion in the form of striations, traces of pressure in the form of surface deformation, and traces of sequencing in the way surfaces intersect and terminate. When these traces are consistent across multiple artifacts, they indicate repeatable workflows. When they appear in multiple regions, separated by geography and culture, but united by material outcomes, they raise profound questions about the universality of certain problem-solving approaches. This does not require invoking anachronistic technologies or speculative machines. It requires acknowledging that ancient artisans may have developed methods optimized for their constraints, methods that achieved results comparable to modern outcomes through different means. The problem arises when modern observers project their own technological dependencies backward and conclude that anything resembling modern precision must have modern origins. This projection blinds us to alternative pathways of innovation. The persistence of impossible precision across ancient stonework forces a reconsideration of how technological capability is defined. If capability is measured solely by the presence of metal tools, written formulas, or mechanized devices, then ancient societies will always appear deficient. But if capability is measured by outcomes, by what was actually achieved in material form, then the picture changes dramatically. The stones themselves argue for a level of understanding that is rarely acknowledged in mainstream narratives. This reframing shifts the burden of explanation. Instead of asking why ancient people would bother to achieve such precision, the more appropriate question becomes how they did so and what systems of knowledge supported it. The fact that these artifacts appear in state-sponsored contexts suggests institutional backing. Large-scale projects require coordination, resource allocation, and oversight. Precision on this scale implies that the governing structures valued accuracy and were capable of sustaining the training and discipline required to produce it. At the same time, the disappearance of these methods highlights the fragility of knowledge transmission. Tools rust, wood decays, and texts burn. But even when all auxiliary evidence is lost, the stone endures. It holds within it the final state of a process, a snapshot of applied understanding. This makes stone uniquely valuable as a historical record. It is not subject to reinterpretation or revision. It simply is what it is, indifferent to our theories. The problem of impossible precision, then, is not merely an archaeological curiosity. It is a challenge to modern assumptions about the relationship between technology, culture, and material achievement. It asks us to take ancient artisans seriously as engineers, not just as craftsmen or ritual specialists. It demands that we read the stone not as decoration, but as evidence. As long as the focus remains on symbolism alone, the engineering story remains untold. But once attention shifts to the physical properties of the artifacts, to their tolerances, symmetries, and surface qualities, a different narrative emerges. One in which ancient societies possessed sophisticated systematic approaches to material manipulation, approaches that were effective enough to leave behind results that still confound us today. In this sense, the stone becomes more than an artifact. It becomes a witness. It bears silent testimony to a mode of knowledge that operated without modern notation, yet achieved modern-level outcomes. The impossible precision carved into ancient stone is not impossible at all. It is simply unexplained within the confines of our current frameworks. And until those frameworks expand to fully engage with the evidence embedded in the material itself, the problem will remain unresolved, waiting patiently in granite, diorite, sandstone, and andesite for someone willing to read it with the seriousness it deserves. Among the most striking material achievements of the ancient world stand the Ashokan pillars of the Mauryan period in India, monumental sandstone columns that rise with serene authority from the landscape and bear inscriptions attributed to Emperor Ashoka in the 3rd century BCE. These pillars are not merely political or religious markers. They are technical artifacts of extraordinary sophistication. What sets them apart is not only their height, mass, or historical significance, but the remarkable surface finish, known as Mauryan polish, often spelled Mauryan polish, a reflective, mirror-like gloss achieved on quartz-rich sandstone. This polish transforms what would otherwise be a granular sedimentary rock into a luminous, almost metallic surface, capable of reflecting light with surprising clarity. It is this finish, preserved across more than 2 millennia, that raises profound engineering questions. Quartz-rich sandstone presents inherent challenges to polishing. Quartz ranks at 7 on the Mohs hardness scale, making it significantly harder than many common minerals and resistant to abrasion. Sandstone itself is a composite material composed primarily of quartz grains bound together by cementing minerals such as silica, calcite, or iron oxides. In addition to quartz, feldspar and mica are often present, each with distinct hardness, cleavage properties, and fracture behaviors. The heterogeneity of sandstone makes uniform finishing extremely difficult. When abrasive force is applied, softer components may erode more quickly than harder ones, leading to micro-pitting, uneven reflectivity, or differential wear. Excessive pressure risks inducing fractures or causing surface chatter, a form of microscopic vibration-induced irregularity. Achieving a mirror-like gloss across such a material requires not only abrasion, but controlled abrasion. Traditional ancient polishing methods are well documented in various cultures. They typically relied on progressively finer natural abrasives, such as sand, emery, crushed quartz, or hematite, combined with water or oil as a lubricant. The logic of progressive abrasion is straightforward. Coarse particles remove larger surface irregularities, while finer particles refine the surface by reducing scratch depth. However, even prolonged manual polishing using such materials tends to leave directional scratches corresponding to the motion of the tool or hand. Uneven reflectivity often results from inconsistent pressure or variation in abrasive particle size. Micro-pitting can occur when grains are dislodged rather than smoothly worn down. These limitations are not theoretical. They are observed in countless manually polished stone surfaces across the world. What makes the Mauryan polish so remarkable is that it appears to transcend these limitations. Scanning electron microscopy studies of Ashokan pillar fragments reveal submicron surface smoothness with almost imperceptible striations. At this scale, the surface approaches optical flatness relative to the grain size of the material. Rather than displaying fractured quartz grains or chipped feldspar edges, the mineral components appear uniformly worn down. Quartz grains are abraded smoothly rather than shattered. Feldspar and mica components exhibit similarly even wear, without the microchipping that would be expected from random or forceful impact. The surface is not simply shiny, it is homogeneously refined. This distinction is crucial. Random abrasion produces randomness in the microstructure. Controlled abrasion produces consistency. When quartz grains are evenly reduced in height relative to surrounding minerals, it implies that pressure, abrasive hardness, and motion were carefully regulated. Too hard and abrasive would gouge or fracture the quartz. Too soft and abrasive would preferentially wear the cement matrix, leaving quartz grains protruding. Too much pressure would induce cracking. Too little would fail to achieve meaningful smoothing. The Mauryan polish suggests a balance point was achieved and maintained across large surface areas. The scale of the pillars amplifies the technical challenge. Many Ashokan pillars exceed 12 meters in height and are carved from single blocks of sandstone. They are cylindrical and exhibit rotational symmetry, meaning that their curvature is consistent around the circumference. Maintaining uniform pressure and motion across such a large vertical surface is non-trivial. Any variation in force application would result in streaking, banding, or localized dullness. Yet the polish appears continuous and uninterrupted, with no visible tool marks, no directional streaking, and no obvious pressure gradients. The absence of these defects implies a high degree of process control sustained over extended durations. One must consider the mechanics of polishing a tall cylindrical column. If performed manually, artisans would need to move around the pillar, applying abrasive slurry with tools or pads. Consistency would require coordination among multiple workers, standardized abrasive mixtures, and possibly rotational manipulation of the pillar itself during finishing. The cylindrical symmetry suggests that either the pillar was rotated relative to a stationary abrasive system or the polishing motion itself was rotationally consistent. In modern manufacturing, rotational symmetry is often achieved using lathes or rotary systems that ensure uniform surface speed and pressure. While it would be anachronistic to assume identical machinery in the Mauryan period, the outcome suggests an equivalent control strategy, whether mechanical or procedural. Experimental replications using historically plausible tools have achieved partial sheen on sandstone surfaces. By employing progressively finer abrasives and dedicating extensive labor hours, researchers have produced surfaces that reflect light to some degree. However, these replications consistently fall short of the depth, uniformity, and homogeneity observed on the original pillars. Directional scratches remain visible under magnification. Reflectivity varies across the surface. Micro-pitting persists in areas where quartz grains resisted uniform wear. The gap between experimental outcomes and archaeological reality is not trivial. It points toward either an optimization of known techniques beyond what has been replicated or the use of process variables not fully accounted for. Modern industrial replication of similar finishes typically relies on aluminum oxide or silicon carbide abrasives, both of which are harder and more consistent than most natural abrasives. These materials are combined with rotary systems that maintain constant pressure and speed, ensuring uniform abrasion across the entire surface. The rotary motion eliminates directional bias in scratch patterns, while controlled feed rates prevent localized overheating or excessive force. Even with such systems, achieving sub-micron smoothness on quartz-rich stone requires careful calibration. The fact that modern industry must resort to such measures to replicate the Mauryan polish underscores the sophistication of the ancient achievement. The absence of visible tool marks on the Ashokan pillars is particularly telling. Tool marks are the fingerprints of process. They reveal direction, speed, and force. Their absence does not imply that no tools were used, but that the finishing stages were refined enough to eliminate or obscure earlier marks completely. This suggests a multi-stage workflow in which coarse shaping was followed by increasingly refined abrasion, culminating in a final polishing phase that erased residual imperfections. The uniformity of the final surface indicates that this workflow was standardized and repeatable. Environmental durability adds another dimension to the analysis. The pillars have endured millennia of exposure to rain, wind, temperature fluctuations, and biological activity. Sandstone is not immune to weathering. Differential erosion typically roughens surfaces over time, especially where mineral components weather at different rates. Yet the Mauryan polish persists in many cases with remarkable integrity. This persistence implies that the surface was not merely smooth superficially, but fundamentally altered in its microtopography. A uniformly abraded surface with reduced microporosity is less susceptible to water infiltration and granular disintegration. In other words, the polish may have enhanced the stone's resistance to environmental degradation. The robustness of the polish reinforces the notion that it was not a decorative afterthought, but a carefully engineered finish. A surface engineered to such smoothness reduces sites for stress concentration and crack initiation. It also minimizes capillary pathways through which moisture can penetrate. Whether ancient artisans understood these effects in theoretical terms is irrelevant. Empirical observation over generations could have revealed that certain polishing methods produced more durable results. The persistence of the polish suggests that whatever method was employed, it was both effective and optimized. The engineering implications of Mauryan polish challenge simplistic narratives about ancient craftsmanship. It is insufficient to attribute the finish to patience or skill alone. Skill must be guided by method. Method must be informed by material behavior. The quartz-rich sandstone of the pillars required a nuanced approach to abrasion, one that accounted for mineral hardness, grain cohesion, and fracture mechanics. The even wear of quartz, feldspar, and mica components indicates that the abrasive medium and applied force were carefully matched to the composite nature of the stone. Rotational symmetry across 12-meter columns further implies that the artisans had a way of ensuring consistent geometry during both shaping and finishing. Cylindricity at that scale cannot be achieved by random effort. It requires reference lines, templates, or rotational guidance. The polish does not merely follow the form, it enhances and preserves it. The reflective surface accentuates deviations, meaning that any irregularity in curvature would be visually amplified. The absence of such distortions suggests that geometric control preceded and accompanied the polishing process. When viewed collectively, these features point toward a highly controlled production environment. The pillars were state-sponsored monuments, commissioned under imperial authority. Such projects would have mobilized skilled labor, standardized procedures, and centralized oversight. The repetition of similar polish across multiple pillars indicates that the technique was not unique to a single artisan, but part of an institutionalized craft tradition. Knowledge was likely transmitted through apprenticeship, refined through practice, and preserved within guild-like structures associated with royal or temple complexes. The mystery deepens when considering the loss of this capability. Later Indian stonework, while often impressive, does not consistently replicate the exact qualities of Mauryan polish. This suggests that the technique was either specific to a particular historical moment or dependent on social and political structures that later dissolved. Technological knowledge is fragile. It depends on continuity of training, patronage, and cultural value. When these conditions change, even highly sophisticated methods can vanish. The Mauryan polish thus stands as both achievement and enigma. It demonstrates that ancient artisans possessed a refined understanding of abrasive processes and material control. It challenges assumptions that pre-industrial societies lacked the means to achieve optical-level finishes on hard stone. And it underscores the importance of reading material outcomes as evidence of process rather than mere ornamentation. Ultimately, the Ashokan pillars are not only historical proclamations carved in stone, they are material testimonies to a level of empirical mastery that rivals modern expectations. The mirror-like gloss of Mauryan polish is not magic, nor is it inexplicable. It is the visible trace of controlled abrasion, sustained pressure regulation, mineralogical awareness, and systematic workflow executed at monumental scale. The pillars rise not just as symbols of moral governance, but as enduring demonstrations of human capacity to refine, control, and perfect the stubborn hardness of quartz-rich stone. Their surfaces continue to reflect light across centuries, and in that reflection lies a challenge to our understanding of ancient technological possibility. The Ashokan pillars and other precisely finished ancient stone artifacts do not merely demonstrate surface refinement, they embody a deeper convergence of geometry, symmetry, and process control. When we examine these works through an engineering lens, rather than solely an artistic or symbolic one, a pattern emerges. The precision of the geometry is inseparable from the control of the process that produced it. The polish, the curvature, the alignment of abrasion marks, and the continuity across complex forms all point toward a systematic approach to material manipulation. The question is not simply how the surfaces became smooth, but how geometric consistency and surface finishing were maintained together across large, hard, and unforgiving stone forms. To achieve uniform polish on tall cylindrical columns requires more than patience or repetitive motion. It requires rotational consistency and evenly distributed abrasive interaction. A cylinder presents a unique geometric challenge. Every point along its circumference must conform to a constant radius relative to a central axis. If the polishing process deviates from this geometry, the error becomes visible. Slight flattening in one region, uneven curvature in another, or inconsistent surface texture disrupts both the visual symmetry and structural integrity. When the surface is mirror polished, as in the Mauryan pillars, deviations become even more pronounced. A reflective finish amplifies irregularities. Light does not forgive error. it exposes it. Uniform polish on such cylindrical forms therefore implies that the artisans maintained consistent relative motion between the abrasive medium and the stone surface. In modern machining, cylindrical symmetry is achieved through rotation about a fixed axis, typically using a lathe. The tool maintains steady contact while the workpiece rotates, ensuring even distribution of material removal. In the absence of mechanized lathes, ancient artisans would have required an alternative strategy. Either the pillar was rotated during finishing, or the polishing motion was applied in a circumferentially controlled manner. In either case, rotational consistency becomes the governing principle. Without it, the polish would reveal unevenness through streaking or directional bias. Hand-driven methods inherently introduce variability. Human operators experience fatigue. Muscular strength fluctuates. Grip changes over time. Tools deform under pressure. Abrasive particles wear down or fracture. Even minor variations in force or angle alter the rate of material removal. Over small surfaces, such variability may average out. Over a 12-meter column, it accumulates. The cumulative effect of uneven pressure would manifest as localized dullness, subtle banding, or microscopic fracture zones in quartz-rich sandstone. Yet such defects are largely absent in the best-preserved examples. Quartz-rich sandstone is particularly unforgiving in this regard. Quartz grains, being hard and brittle, respond to uneven stress with fracture rather than plastic deformation. If pressure exceeds a certain threshold or is applied at inconsistent angles, microfractures propagate along grain boundaries. These fractures produce surface roughness that is difficult to eliminate without further controlled abrasion. The presence of evenly worn quartz grains on Ashokan pillars indicates that the applied pressure remained within a narrow operational window. Too little force would fail to reduce surface asperities. Too much would shatter grain edges. The artisans appear to have navigated this window with remarkable stability. The role of tool deformation must also be considered. Natural abrasives embedded in pads or cloth surfaces do not maintain perfectly uniform geometry. As they wear, they develop irregularities. A rigid tool pressed unevenly against a cylindrical surface would preferentially abrade high points, gradually altering curvature. Maintaining geometric integrity would therefore require periodic adjustment, possibly reshaping of polishing implements, and careful monitoring of surface development. The final surfaces suggest that such monitoring occurred consistently. Scanning electron microscopy adds another layer of insight. SEM imaging of polished sandstone surfaces reveals abrasion patterns that appear aligned and systematic. Rather than random scratch orientations typical of uncontrolled manual polishing, the striations exhibit coherence. They follow discernible paths, often subtle and evenly distributed. This alignment suggests that motion during polishing was not arbitrary. It followed a predefined trajectory, whether circumferential, helical, or oscillatory. Systematic alignment of microstriations implies repetition of motion with controlled parameters. It is the microscopic signature of workflow discipline. The systematic nature of abrasion patterns extends beyond simple cylindrical shafts. The capitals atop Ashokan pillars, often carved in elaborate forms such as lions or lotuses, display continuity of finish across curved and fluted geometries. Fluting introduces alternating concave and convex surfaces. Maintaining uniform polish across such varied curvature requires adaptive control. Abrasive contact area changes with curvature. Pressure distribution shifts. On concave surfaces, excessive force concentrates along edges. On convex surfaces, it disperses. The fact that polish consistency extends across these transitions suggests that artisans adjusted their approach dynamically, anticipating how friction would interact with each geometric feature. Such adaptability indicates more than intuitive craftsmanship. It reflects a conceptual understanding of material response to friction and stress. Friction generates localized heat and mechanical interaction at the grain scale. In quartz-rich sandstone, Excessive localized heat or stress concentration could initiate microcracking. The absence of widespread microchipping implies that artisans controlled not only force, but also motion speed and perhaps lubrication. Water or oil used as a medium would reduce frictional spikes and distribute abrasive particles more evenly. The selection and maintenance of such slurry mixtures would have been integral to process control. The artisans appear to have anticipated the behavior of mineral grains under abrasion. Quartz, feldspar, and mica differ in hardness and cleavage. If a surface is abraded without regard to these differences, softer minerals erode more rapidly, leaving harder grains protruding. Protruding grains then experience higher stress during subsequent passes, increasing fracture risk. The evenly worn mineral profile observed in polished pillars suggests that abrasive hardness was calibrated to engage all components effectively. The abrasive medium must have been harder than quartz, yet fine enough to avoid gouging. Its particle size distribution would need to be consistent to prevent random deep scratches. Anticipation of grain behavior also implies sequencing of operations. Coarse shaping likely preceded fine polishing. After shaping, residual surface irregularities would have included microfractures and tool marks. Before final polishing, intermediate smoothing would have reduced these features to a scale manageable by fine abrasives. Skipping intermediate stages would leave defects too deep to eliminate efficiently. The final polish is therefore the visible outcome of a multi-stage process in which each stage prepared the surface for the next. This layered workflow mirrors modern surface finishing protocols. The absence of visible tool marks on finished surfaces underscores the success of this sequencing. Tool marks from shaping, whether from chisels, hammerstones, or abrasion blocks, would typically remain detectable under magnification. Their absence indicates that finishing stages removed them entirely. This requires consistent depth of material removal across the entire surface. Removing too much would distort geometry. Removing too little would leave residual traces. Maintaining the balance demands process awareness. Symmetry in these pillars is not purely aesthetic, it is structural. A cylindrical column distributes load evenly along its axis. Deviations from symmetry introduce stress concentrations. While the pillars primarily functioned as monuments rather than load-bearing architectural elements, structural stability remains relevant. A tall, slender column must resist bending forces from wind or minor seismic activity. Uniform cross-sectional geometry contributes to predictable stress distribution. The preservation of geometric symmetry therefore suggests attention not only to visual harmony, but to mechanical reliability. Hand-driven methods are constrained by human physiology. Fatigue affects pressure consistency. Extended repetitive motion introduces variability. The sheer duration required to polish a 12-meter column to sub-micron smoothness would test endurance. This implies organized labor, possibly rotating teams of artisans maintaining consistent technique. Process control in such contexts becomes social as well as mechanical. Standards must be shared. Methods must be taught. Supervisory oversight may have ensured adherence to established procedures. Even minor deviations in angle during polishing can create localized fractures in quartz-rich sandstone. If an abrasive pad contacts the surface at an inconsistent angle, force distribution shifts toward a smaller contact area, increasing stress per unit area. At the grain scale, this can exceed fracture thresholds. The relative absence of such microfractures indicates stable contact geometry. This stability could have been achieved through shaped polishing implements that conform to curvature, or through controlled body positioning techniques refined through apprenticeship. The consistency observed across multiple pillars implies standardization. It is unlikely that each pillar was polished by entirely independent, improvising individuals. The similarity of finish across geographically dispersed examples suggests a shared method. This standardization is a hallmark of process control. It indicates that knowledge was codified, even if not written. Codification may have existed in the form of oral instruction, demonstration, and ritualized practice. The lack of surviving written manuals or diagrams does not negate the existence of procedural knowledge. It merely shifts the evidence from text to material outcome. The finished stone becomes the primary documentation. Each aligned striation, each uniformly worn grain, each uninterrupted reflective band is a record of motion and force applied in the past. The geometry of the pillar encodes decisions about axis alignment, curvature control, and finishing sequence. The symmetry reflects measurement strategies, whether through string lines, plumb bobs, templates, or rotational reference systems. The polish records abrasive selection, lubrication control, and pressure modulation. The interplay between geometry and surface finish is critical. A surface may be smooth yet geometrically distorted, or geometrically accurate yet rough. The Ashokan pillars achieve both. This dual achievement indicates integration of shaping and finishing processes. Geometric control likely preceded fine polishing, but fine polishing reinforced and revealed geometric accuracy. Any residual asymmetry would become evident once reflectivity increased. The fact that reflectivity appears uniform suggests that geometric tolerances were already tight before final finishing. Consider also the curved transitions between shaft and capital. These areas involve changes in diameter and curvature. Maintaining smooth transitions without flat spots or abrupt changes requires continuous monitoring. Abrasive interaction must adapt to curvature gradients. Excess pressure at transition zones would produce visible distortions. The continuity observed implies real-time feedback, visual, tactile, or both, guiding artisans during polishing. This feedback loop is central to process control. It transforms polishing from brute force abrasion into controlled material refinement. In the absence of written documentation, we are left to infer method from result. The pillars speak through their surfaces. The systematic alignment of micro-abrasion patterns, the preservation of rotational symmetry, and the uniformity across complex geometries collectively suggest that ancient artisans operated within a conceptual framework of material behavior. They may not have articulated friction coefficients or fracture mechanics in formal terms, but they understood through practice how stone responded to force. Such understanding likely evolved over generations. Repeated attempts would reveal patterns. Excessive pressure produces chipping, uneven motion produces streaks, inconsistent abrasive mixtures yield irregular sheen. Through trial, observation, and refinement, a stable protocol emerges. Once stabilized, it can be transmitted. Apprentices learn not just what to do, but what to avoid. They internalize thresholds. How much pressure is too much, how fine and abrasive is fine enough, how long to persist at each stage. The pillars therefore embody both geometry and discipline. Geometry provides the target, cylindricity, symmetry, curvature. Discipline ensures the path, controlled motion, regulated pressure, sequential abrasion. Together they produce the extraordinary surfaces that have endured for millennia. Ultimately, the absence of written manuals heightens rather than diminishes the significance of these artifacts. The finished stone stands as the only surviving manual. It contains within its microtopography the history of its making. The artisans who shaped and polished these pillars left no diagrams, no theoretical treatises. Yet their understanding is visible in every aligned striation and every uninterrupted reflective plane. Geometry, symmetry, and process control converge in these monuments, revealing a tradition of material mastery grounded in empirical knowledge and executed with remarkable consistency. In studying these pillars, we are not merely observing polished stone. We are witnessing the residue of controlled motion, managed stress, and systematic reasoning applied to one of nature's most resistant materials. The pillars remain silent, but their geometry and surfaces testify to a level of process awareness that challenges assumptions about pre-industrial capability. Through careful measurement and analysis, modern observers can begin to reconstruct the logic embedded in the stone, a logic that integrates form, friction, and force into a unified practice of precision. The dominant archaeological explanation for ancient hard stone working rests on a principle that is both elegant and materially grounded: abrasive slurry technology. Rather than proposing lost alloys, exotic machinery, or anachronistic tools, the orthodox model argues that ancient artisans achieved remarkable results using simple materials arranged in intelligent combinations. At the center of this explanation lies a crucial distinction. The cutting was not performed primarily by the metal tools themselves. It was performed by abrasive particles harder than the stone being shaped. The metal served as a carrier, a holder, a guide. The real work was done by grains of quartz, emery, corundum, or similar hard minerals suspended in a fluid medium. This model begins with a straightforward physical reality. Granite, diorite, and quartz-rich sandstone are significantly harder than copper. On the Mohs scale of mineral hardness, copper ranks around 3, while quartz ranks at 7, and corundum approaches 9. If one were to press a pure copper chisel directly against granite, the copper would deform long before the granite yielded. The stone would remain largely unaffected except for minor bruising. Therefore, if ancient Egyptians, Indians, or Andean builders were shaping such stones, the metal tools alone could not have been responsible for cutting. The orthodox solution is to introduce abrasives harder than the stone. In abrasive slurry technology, soft metal tools such as copper chisels, saws, or tubular drills act as carriers for harder abrasive particles. These tools provide shape, direction, and containment. The abrasives provide hardness and cutting action. When abrasive particles are trapped between the tool and the stone surface, they function as countless microscopic cutting edges. Under pressure and motion, each grain scratches, fractures, or plows through the stone's crystalline structure. Material is gradually removed not by the tool's edge, but by the abrasive grains rolling, sliding, and embedding at the interface. The use of abrasives such as quartz sand, emery, or corundum is well documented in ancient contexts. Quartz sand is abundant in many regions, particularly in Egypt. Emery, a natural mixture containing corundum and other hard minerals, was known in antiquity and used for grinding and polishing. Corundum itself, with a hardness second only to diamond among common minerals, is capable of abrading quartz and feldspar effectively. These materials would have been recognized empirically as effective grinding agents long before formal mineralogy existed. Water or oil serves a critical role in this system. It acts as a lubricant, reducing friction spikes that might cause tool seizure or uncontrolled fracture. It suspends abrasive particles, allowing them to circulate within the cutting zone. It also assists in removing debris, flushing away pulverized stone and worn abrasive grains so that fresh cutting edges can engage the surface. Without a fluid medium, abrasive grains would quickly clog, overheat, or embed unevenly, reducing efficiency and increasing the risk of surface damage. The physics of abrasive slurry machining is not speculative. It is consistent with modern grinding processes. In contemporary industry, lapping and grinding operations rely on similar principles. A relatively soft lap plate holds abrasive slurry. The abrasive particles do the cutting. The plate provides conformity and motion control. Ancient artisans within the orthodox framework are understood to have applied an early version of this principle using available materials and manual power. Experimental archaeology has played a significant role in validating this model. Researchers have reconstructed copper tube drills consistent with archaeological finds. These tubular drills, when used with abrasive slurry, have successfully penetrated granite and diorite. The principle is straightforward. A hollow copper tube is pressed against the stone while rotating. Abrasive slurry is introduced at the interface. As the tube rotates, abrasive grains trapped between the tube edge and the stone cut into the material. Over time, a circular groove deepens. The interior portion of the stone remains intact, forming a cylindrical core. Replication experiments have indeed produced cylindrical cores similar to those found in Egyptian quarries and archaeological sites. Shallow cavities, flat surfaces, and drilled holes have been demonstrated using plausible ancient tools. Bow drills, Weighted vertical drills and manually rotated systems have all been employed in controlled experiments. The results confirm that granite is not immune to copper-based tooling when abrasives are properly used. Material removal is slow but measurable. With sufficient labor and time, significant penetration can be achieved. Spiral striations observed on drilled cores, long noted by archaeologists and engineers, can also be explained within this framework. When a tubular drill rotates while being fed downward, the abrasive contact zone advances into the stone. If the downward feed is continuous and rotation is steady, the abrasive path traces a helical pattern along the core. Each rotation removes a thin ring of material slightly deeper than the previous one. The resulting spiral is the geometric consequence of rotational motion combined with vertical descent. The pitch of the spiral, the distance between successive turns, reflects the relationship between rotational speed and downward feed rate. A faster downward feed relative to rotation produces a wider spiral pitch. Slower feed produces tighter spirals. Variability in pressure or motion leads to irregular pitch. Within the orthodox model, the presence of spiral striations is not mysterious. It is expected. It is the natural signature of rotary abrasive drilling. Archaeological evidence supporting this model includes the discovery of copper tools, abrasive residues, and unfinished stone objects. Copper chisels, saw fragments, drill bits, and tubular drill remains have been recovered from Egyptian sites. Residues consistent with abrasive materials have been identified in workshop contexts. Unfinished vessels and partially drilled cores provide snapshots of work in progress. These artifacts form a material chain linking tool, abrasive, and stone. The presence of unfinished objects is particularly important. They demonstrate intermediate stages of production. Partially drilled holes show concentric grooves consistent with tubular drilling. Rough-shaped vessels display tool marks that correspond to abrasion rather than percussion alone. These transitional pieces reduce the need for speculative explanations. They show process rather than just outcome. In the orthodox interpretation, ancient stoneworking was labor-intensive, but not technologically mysterious. Time and organization compensate for the relative softness of copper. A workforce of trained artisans applying abrasive slurry over extended periods can gradually shape even the hardest stones. State-sponsored projects, such as those in Egypt or Mauryan India, had access to large labor pools and centralized resource management. The investment of time would have been justified by political or religious objectives. The efficiency of abrasive slurry machining depends on several controllable variables: abrasive hardness, particle size, slurry concentration, applied pressure, and motion speed. Ancient artisans may not have expressed these in mathematical terms, but through repeated practice they would have learned optimal combinations. Too coarse an abrasive leaf deep scratch, too fine an abrasive removes material slowly. Insufficient slurry leads to clogging. Excess slurry dilutes cutting action. Effective stoneworking would have required balancing these factors. Flat surfaces, such as those seen in certain Egyptian blocks or Andean stones, can also be produced through abrasive techniques. A flat copper saw blade combined with abrasive slurry can gradually cut along a straight path. The blade does not slice like a steel saw, it acts as a guide for abrasive particles. The resulting kerf width corresponds to blade thickness and abrasive action. Repeated passes deepen the cut. Eventually, the stone separates along the cut line. Similarly, flat polishing can be achieved by rubbing a stone surface against a flat abrasive charged plate. Over time, high points are reduced. The surface approaches planarity. This is analogous to modern lapping, where two surfaces are rubbed together with abrasive slurry to achieve flatness. The process is slow but effective. The more rigid and stable the setup, the more consistent the result. Within the orthodox framework, the extraordinary polish of certain artifacts is seen as the cumulative result of progressive abrasion. Coarse shaping removes bulk material. Medium abrasives refine the surface. Fine abrasives produce sheen. Final burnishing may further smooth micro-asperities. Each stage builds upon the previous one. There is no need to invoke advanced alloys or mechanical motors. The explanation relies on known physical principles and materials available in antiquity. Critically, the orthodox model does not deny the sophistication of ancient artisans. On the contrary, it emphasizes their empirical mastery. Understanding that copper could act as a carrier for harder particles represents a practical insight into composite tooling. Recognizing that slurry lubrication improves efficiency reflects observational learning. Organizing labor to sustain prolonged grinding operations indicates logistical capability. The model also accounts for variability. Not all ancient stonework displays extreme precision. Many examples show irregularities, tool marks, and asymmetries. This variability is consistent with manual abrasive processes. It suggests a spectrum of skill and investment rather than universal perfection. High-precision pieces may represent elite workshops or especially well-executed projects within a broader technological context. Furthermore, abrasive slurry technology aligns with a broader pattern of ancient manufacturing techniques. In many cultures, grinding and polishing were central to tool-making and ornament production. Stone axes, beads, and statues were shaped through abrasion long before metalworking matured. Extending this approach to larger architectural or ceremonial objects is a logical progression rather than a technological leap. One of the strengths of the orthodox model lies in its reliance on experimentally reproducible principles. Modern researchers can test hypotheses by recreating tools and applying abrasive slurry under controlled conditions. When granite is penetrated using copper tubes and quartz sand, the physical plausibility of the method is demonstrated. Even if ancient artisans optimized the process beyond modern replication attempts, the foundational mechanism remains sound. The presence of spiral striations, cylindrical cores, and abrasive residues forms a coherent explanatory cluster. Each piece of evidence supports the others. The spirals reflect rotary abrasive drilling. The cores demonstrate tubular cutting. The residues confirm abrasive use. The copper tools provide the carriers. Together, they create a closed loop of interpretation grounded in material findings. Time remains a central factor in this model. Abrasive machining is inherently slow compared to modern cutting tools. Producing deep holes or extensive polished surfaces would have required patience and sustained effort. However, ancient societies undertaking monumental projects often operated on timescales measured in decades rather than months. Labor investment was not constrained by modern economic assumptions about efficiency. The orthodox explanation also accommodates environmental durability. Surfaces polished through fine abrasion can achieve low roughness, reducing sites for moisture retention and chemical weathering. The long-term persistence of certain polished surfaces is therefore consistent with abrasive finishing rather than contradictory to it. The abrasive slurry model provides a coherent, materially grounded explanation for ancient hard stone working. It asserts that soft metal tools acted as carriers for harder abrasive particles. It identifies quartz, emery, and corundum as plausible cutting agents. It explains the role of water or oil in lubrication and debris removal. It accounts for spiral striations through the geometry of rotary motion and feed. It is supported by archaeological evidence in the form of copper tools, abrasive residues, and unfinished objects. And it has been partially validated through experimental archaeology, demonstrating that granite and diorite can indeed be shaped using these methods. Within this framework, ancient stone working appears not as an impossible anomaly, but as the outcome of intelligent application of simple physical principles. The extraordinary results are attributed to time, organization, and empirical refinement rather than lost technology. Whether this model fully explains every observed precision is a matter for continued investigation, but as the dominant archaeological explanation, abrasive slurry technology remains the cornerstone of orthodox understanding of ancient hard stone craftsmanship. The orthodox model of abrasive slurry machining provides a physically plausible explanation for how ancient artisans could shape hard stone using relatively soft metal tools. It demonstrates that copper, when combined with harder abrasive particles and a lubricating medium, can gradually remove material from granite, diorite, and quartz-rich sandstone. Experimental archaeology confirms that drilling, cutting, and polishing are possible under these conditions. Yet possibility is not the same as scalability, repeatability, or extreme precision. When the focus shifts from whether stone can be shaped to how consistently and accurately it can be shaped under purely manual conditions, the limitations of abrasive slurry technology begin to emerge with increasing clarity. At the center of these limitations lies the human body itself. Human operators cannot maintain perfectly consistent pressure or motion over extended periods. Even the most disciplined artisan experiences micro-variations in muscular output. The application of force through the hands and arms is never mathematically uniform. Each rotation of a drill, each forward stroke of a saw, each polishing pass carries subtle fluctuations in pressure, angle, and speed. These fluctuations are small, often imperceptible to the naked eye during the act of working. But when multiplied across thousands of repetitions, especially in hard and brittle materials, they accumulate into measurable deviations. Fatigue is not a minor factor in abrasive stoneworking. It is central to understanding its limitations. Sustained drilling into granite with a copper tube and abrasive slurry demands continuous downward force combined with rotational motion. Over time, wrist strain develops. The small stabilizing muscles in the forearm fatigue. Grip strength declines. As fatigue increases, pressure becomes inconsistent. The operator unconsciously shifts posture to relieve strain, altering the angle of force application. These small adjustments introduce asymmetry into the cutting interface. In shallow operations, such variability may be manageable. In deeper penetrations, the consequences amplify. Copper tools themselves contribute to this instability. Copper is relatively soft and ductile. Under sustained pressure, it bends. Tubular drills can deform slightly at their cutting edge. If one side of the tube experiences marginally higher resistance due to stone heterogeneity or abrasive concentration, that side may compress or flare differently. Wooden shafts used to drive drills introduce further compliance. Wood flexes under load. Even slight bending at the shaft translates into misalignment at the cutting interface. As depth increases, the effective lever arm grows, magnifying any small angular deviation at the top into a larger eccentricity at the bottom. Maintaining coaxiality in deep drilling operations is therefore inherently difficult. Coaxiality refers to the alignment of the drilling axis such that the hole remains centered and circular along its entire depth. In a perfectly controlled system, the drill rotates around a fixed axis and descends uniformly. In manual systems, the axis can wander. Slight tilting produces elliptical tendencies. Uneven abrasive distribution can cause preferential cutting on one side. As the hole deepens, correcting these deviations becomes increasingly challenging because the operator loses direct visibility of the cutting interface. The deeper the hole, the more it behaves like a guide that constrains the tool, but if misalignment has already occurred, the constraint may lock in imperfection rather than eliminate it. Uniform wall thickness presents a related challenge, particularly in hollow stone vessels or drilled cores. If the external shape of a vessel is established first and the interior is drilled later, maintaining a consistent wall thickness requires precise control of depth and lateral position. Without modern gauges or real-time feedback, artisans would rely on tactile cues, sound, and experience. However, tactile feedback diminishes as the tool penetrates deeper. Sound transmission through slurry and stone is diffuse. Measuring internal thickness without breaching the wall becomes a matter of estimation. Any slight overcut on one side risks thinning the wall unevenly. In brittle materials, Thin sections are prone to fracture. Replication experiments consistently reveal these difficulties. While abrasive slurry can indeed smooth surfaces and produce symmetrical forms, mirror-like polish and tight internal symmetry remain elusive under purely manual conditions. Experimental surfaces often display micro-chatter, tiny irregularities caused by intermittent abrasive engagement. When pressure fluctuates, abrasive grains alternately bite and release, creating microscopic undulations. Under magnification, these appear as small pits or shallow grooves. Reflectivity becomes uneven because surface roughness varies across micro-regions. True mirror-like gloss requires not only low average roughness, but uniform roughness distribution. Manual polishing struggles to maintain such uniformity across large areas. Circularity is another measurable parameter. A hole that appears round to the naked eye may deviate from perfect circularity when measured with precision instruments. Small deviations from circularity arise from asymmetric force application, uneven abrasive concentration, and tool flex. In experimental archaeology, drilled holes often exhibit slight ovalization or tapering. These deviations may be acceptable for functional purposes, but when archaeological artifacts display extremely tight symmetry, the question shifts from possibility to consistency. Scaling abrasive slurry methods to entire structures or to the production of large numbers of identical objects introduces additional constraints. Each operation is slow. Material removal rates are limited by abrasive hardness, particle size, and applied pressure. Increasing pressure risks tool deformation or stone fracture. Increasing abrasive coarseness increases scratch depth and reduces surface quality. Therefore, achieving both efficiency and high finish quality requires sequential stages. Rough shaping, intermediate refinement, and fine polishing must be performed in order. Each stage consumes time. Some estimates derived from replication studies suggest that drilling a single deep granite hole using copper tube and abrasive slurry can require many days of continuous labor. Polishing large surfaces to high sheen can take weeks. If a single object demands such investment, producing multiple identical objects multiplies the labor accordingly. State-sponsored workshops could marshal large workforces, but coordination becomes a factor. Different workers applying slightly different pressures or motions introduce variability between pieces. Achieving near-identical symmetry across multiple artifacts under these constraints becomes increasingly demanding. Hidden surfaces introduce perhaps the most intriguing challenge. In many ancient stone vessels, the interior surfaces exhibit precision and smoothness comparable to exterior surfaces, despite being largely invisible during finishing. The bottoms of drilled cores show consistent geometry, even though they are not directly observable during the drilling process. Without visual feedback, artisans must rely entirely on mechanical guidance and process stability. In manual systems, feedback loops are slower and less precise. Deviations may not be detected until significant material has already been removed. Consider the bottom of a drilled cavity. As a tubular drill advances, the interior core remains attached to the base until final breakthrough or extraction. The flatness or geometry of the bottom surface depends on uniform abrasive engagement across the circumference. If pressure is uneven, one side may cut deeper. In shallow cavities, corrections are possible. In deep cavities, the interior becomes increasingly inaccessible. Maintaining precision under such blind conditions requires extraordinary consistency. Mirror-like polish presents its own set of constraints. Abrasive slurry can smooth surfaces effectively, but achieving a gloss that approaches specular reflection requires reducing surface roughness to sub-micron levels. Each polishing stage must remove the scratches from the previous stage without introducing new irregularities. Manual polishing introduces directional bias because the motion of the hand has a preferred orientation. Even when artisans attempt cross-hatching techniques, microstriations often remain. Uneven reflectivity emerges because pressure is rarely distributed perfectly evenly across curved or vertical surfaces. Furthermore, quartz-rich materials are brittle. Minor deviations in pressure or angle can initiate microfractures. These fractures may be too small to see without magnification, but can disrupt surface uniformity. The artisan must balance sufficient force to remove material against the risk of inducing subsurface damage. This balancing act becomes increasingly delicate as the desired finish approaches high polish. When considering entire structures, such as large pillars or monumental stone blocks, the cumulative effect of these limitations becomes more pronounced. Maintaining consistent pressure across a 12-meter cylindrical column requires not only stamina, but coordination. If polishing is performed in segments, transitions between segments risk visible boundaries. If multiple workers operate simultaneously, synchronizing force and motion becomes complex. Even slight differences in technique can produce subtle surface variation. Time investment further complicates the picture. Weeks or months of continuous labor for a single object is not inconceivable in ancient state contexts. However, sustained high-quality output over extended periods demands logistical stability. Workers must be trained to consistent standards, abrasive supplies must be replenished, tools must be maintained and reshaped, copper edges wear and must be hammered back into shape. Each maintenance event introduces potential geometric change. Maintaining process continuity across these interruptions requires careful management. Manual methods also struggle with cumulative error. Each stage of shaping depends on the accuracy of the previous stage. If a slight asymmetry is introduced during rough shaping, subsequent polishing may refine the surface without correcting the underlying geometric deviation. The result is a beautifully smooth surface that is subtly off-axis. Detecting and correcting such deviations without precision measuring instruments is difficult. The absence of rigid mechanical constraints exacerbates these issues. Modern drilling systems rely on guide rails, bearings, and fixed frames to maintain alignment. Manual systems depend on human steadiness and simple supports. While jigs and braces may have been used in antiquity, evidence for highly rigid, precision-aligned frameworks is limited. Without such frameworks, maintaining perfect perpendicularity or concentricity over large scales becomes increasingly improbable. In replication experiments, researchers frequently report that while basic forms are achievable, the depth, uniformity, and homogeneity of certain ancient finishes remain difficult to reproduce. Surfaces can be polished to sheen, but achieving the same level of reflectivity across complex geometries requires extraordinary care. Micro-pitting and minor chatter persist. Slight deviations from circularity are common. These experimental outcomes do not invalidate the abrasive slurry model, but highlight its operational limits. The problem intensifies when perfection appears to be maintained repeatedly. A single exceptional artifact might be attributed to an unusually skilled artisan or extraordinary patience. Multiple artifacts exhibiting similar precision suggest either a highly standardized process or a control mechanism that minimizes variability. Manual abrasive systems inherently contain variability. Reducing that variability to negligible levels across repeated productions requires either extreme discipline or additional mechanical stabilization. Thus, while abrasive slurry technology explains the mechanism of material removal, the limits of human labor introduce constraints on precision, repeatability, and scale. Human operators cannot sustain perfectly uniform pressure indefinitely. Fatigue alters motion, copper bends, wooden shafts flex, misalignment increases with depth. Microchatter and uneven reflectivity emerge under magnification. Hidden surfaces lack direct feedback. Scaling production multiplies time investment and coordination challenges. These constraints do not render ancient achievements impossible. Rather, they frame the problem more sharply. The question is not whether abrasive slurry can cut stone, it can. The question is how ancient artisans managed, within the physical limits of human musculature and compliant tools, to achieve and repeat results that in some cases approach geometric and surface precision beyond what modern manual replication easily attains. Understanding these limits is essential because only by defining the boundaries of the orthodox method can one evaluate whether the observed artifacts fall comfortably within them or press against their outer edge. One of the most compelling dimensions of ancient high-precision stonework emerges not on the visible exterior surfaces that catch the eye, but in the hidden geometries that lie beyond immediate human perception. In artifact after artifact across Egypt, India, and the Andes, the most astonishing features are not merely polished outer faces or visually impressive alignments, but internal symmetries and surface qualities preserved in areas inaccessible to direct observation during manufacture. These are regions where the artisan could not continuously see the cutting interface, could not easily measure deviation in real time, and could not directly observe the cumulative effects of minute variations in pressure, angle, or abrasive distribution. Yet in many cases, the geometry remains controlled, consistent, and surprisingly precise. Consider the interiors of ancient stone vessels, particularly those carved from granite, diorite, or other hard crystalline materials. These vessels often possess narrow necks and wider internal cavities, creating shapes that restrict both light and physical access. Once the opening is defined, the interior becomes progressively concealed as depth increases. Despite this, measurements taken in modern analyses frequently reveal that interior walls maintain concentricity relative to the exterior form. The curvature does not wander erratically. Wall thickness, in some examples, remains consistent within narrow tolerances around the entire circumference. The internal surface follows a predictable geometric path rather than reflecting the stochastic variability one might expect from purely manual hand-driven abrasion. Concentricity is not a trivial property. To maintain it throughout the depth of a vessel requires that the axis of interior removal remain aligned with the exterior reference axis. Any deviation in drill orientation, even slight tilting during early stages, would propagate downward as the cavity deepens. Once a misalignment occurs, correcting it without widening the cavity excessively or thinning one side disproportionately becomes extremely difficult. The deeper the interior, the more constrained the tool becomes by the existing cavity walls. If asymmetry is introduced early, it tends to be amplified rather than corrected. Yet many ancient vessels demonstrate interiors that appear to track the central axis with remarkable stability. Surface quality within these interiors compounds the mystery. Under magnification, some internal surfaces exhibit smoothness and regularity comparable to or approaching that of exterior faces. The presence of uniform curvature suggests consistent abrasive interaction along the entire internal circumference. Achieving such uniformity manually requires the operator to apply even pressure in a circular motion while lacking direct visual confirmation of tool engagement across all points of contact. In narrow-necked vessels, the artisan's line of sight is limited to the upper region. The lower interior remains effectively blind during active shaping. The process must therefore rely on indirect feedback, vibration, sound, resistance rather than sight. Indirect feedback, however, is inherently less precise and slower to reveal small deviations. Interlocking stone blocks present a parallel phenomenon. In Andean architecture, for example, large stones fit together with tight tolerances not only on their visible faces, but on concealed contact surfaces. Once assembled, these surfaces are hidden from view. Yet their fit contributes to structural stability and the absence of gaps. Achieving such fit requires shaping multiple planes so that they correspond to complementary surfaces on adjacent blocks. The artisan cannot fully evaluate concealed faces once installation occurs. Therefore, the shaping process must anticipate and control contact geometry before final placement. Small deviations in angle or curvature would manifest as gaps or instability. The precision observed implies a high degree of process control extending beyond superficial aesthetics. As geometry becomes deeper or more concealed, the plausibility of purely manual control decreases. Manual systems depend heavily on visual feedback for fine correction. The human eye detects asymmetry, unevenness, or irregular reflection on exposed surfaces and guides the hand accordingly. Remove visual access, and correction becomes reactive rather than proactive. Deviations may accumulate before being detected. In shallow operations, correction is manageable. In deep or enclosed geometries, correction often requires removing additional material, potentially compromising symmetry or thickness. The more hidden the geometry, the more difficult it becomes to maintain perfection through iterative adjustment. Replication experiments illuminate these constraints with practical clarity. Experimental archaeologists have demonstrated that drilling and hollowing are achievable using copper tools and abrasive slurry. However, when attempting to reproduce the internal concentricity and surface uniformity of certain ancient vessels, results often diverge from the archaeological originals. Interiors may appear smooth to casual inspection, but reveal slight eccentricity under measurement. Wall thickness may vary subtly around the circumference. Microchatter or shallow irregularities persist on interior surfaces. These deviations are not catastrophic. They are small, but measurable. They reveal the inherent variability introduced by manual control and tool compliance. Experimental teams frequently acknowledge that their successes are partial and principle-based rather than fully equivalent. The principle that abrasive particle carried by a soft metal tool can remove hard stone is validated. Basic forms can be reproduced, spiral drill marks can be generated, cavities can be hollowed. Yet achieving the full precision observed in some archaeological specimens remains elusive. Replication often demonstrates feasibility without achieving equivalence. The difference between possible and identical becomes the critical gap. This gap is not merely academic, it highlights the distinction between theoretical plausibility and empirical reproduction. A method may explain how material removal occurs in theory, but unless it consistently produces results matching the archaeological record in measurable detail, questions remain. In the case of hidden geometries, the discrepancy becomes more pronounced. If manual methods inherently introduce micro-variability and cumulative deviation, and if such deviation is not evident in certain ancient artifacts, then either the artisans operated at extraordinary levels of discipline and consistency, or additional stabilizing factors were present. One possible explanation is the use of guiding fixtures or rotational supports that constrained tool motion. Even simple supports can dramatically improve alignment. However, direct archaeological evidence for rigid precision guiding frameworks in some contexts is sparse. Another possibility is extended time investment combined with iterative measurement techniques using templates or gauges. Yet measuring internal geometry deep within a cavity without specialized instruments presents challenges. Templates must fit within narrow openings and provide reliable reference points. Each measurement requires removal and reinsertion, introducing opportunities for disturbance. The issue becomes even more striking when considering repeated production. A single vessel with exceptional internal symmetry might be attributed to rare skill or extraordinary patience. Multiple vessels exhibiting similar internal consistency suggest a systematic process capable of minimizing deviation across iterations. Systematic processes generally require either mechanical stabilization or standardized protocols that reduce operator variability. Purely freehand manual abrasion, subject to fatigue and tool flex, inherently resists such standardization at micron-level tolerances. Concealed faces of interlocking blocks present similar constraints. Achieving tight tolerances on surfaces that will ultimately be hidden requires pre-assembly testing and iterative refinement. Each cycle of placement and removal risks altering adjacent surfaces. Maintaining alignment across multiple faces simultaneously is geometrically complex. When blocks fit so tightly that a blade cannot easily penetrate the seam, even on concealed interfaces, the level of predictive control implied is substantial. The deeper philosophical implication of precision, where the eye cannot see, is that aesthetic motivation alone cannot account for it. Exterior polish may serve symbolic or visual purposes. Hidden interior symmetry does not enhance visual impact. Its presence suggests that precision was embedded within the process itself rather than applied solely for display. The artisans, intentionally or as a byproduct of their technique, achieved uniformity independent of immediate visual reward. This indicates either a cultural valuation of unseen perfection or, more mechanically, a process that naturally produced high regularity throughout the geometry. The unresolved tension lies in the persistent gap between what replication can demonstrate in principle and what archaeological artifacts display in practice. Experimental archaeologists do not deny this gap. Rather, they contextualize it. They acknowledge that their reconstructions approximate ancient methods, but may not capture all variables. Unknown refinements in abrasive preparation, tool geometry, lubrication, or workshop organization could have enhanced stability and control. At the same time, the absence of fully equivalent replication leaves open the question of whether current models fully encompass the operational sophistication of ancient techniques. Thus, precision in unseen regions becomes a diagnostic feature. It tests the robustness of explanatory models under conditions of reduced feedback and increased geometric constraint. When internal concentricity persists despite lack of visual guidance, when concealed block faces align with tight tolerances, when interior surfaces approach the smoothness of exterior ones, the demands placed on manual control intensify. The deeper the geometry and the more hidden the surface, the more extraordinary the consistency appears. The gap between theoretical plausibility and empirical replication remains unresolved because theory establishes that stone can be shaped by abrasive slurry, but empirical replication has yet to reproduce, in all cases, the full suite of precision characteristics observed in certain ancient artifacts. Until that gap is either narrowed through more advanced reconstructions or convincingly explained through documented process refinements, the question remains open. The stone preserves the outcome, the method remains partially reconstructed, and in the silent interiors where no eye could see during manufacture, the geometry continues to testify to a level of control that challenges simple assumptions about the limits of manual labor alone. The dominant explanation for ancient hard stone working remains abrasive slurry technology, and it occupies this position not only because it is experimentally supported, but because it represents the most conservative and methodologically secure interpretation available. In archaeology, the safest explanation is the one that requires the fewest new assumptions. Abrasive slurry machining fits comfortably within known material science principles. It requires no lost machines, no speculative energy sources, no unknown physics. Copper tools, hard abrasive particles, lubrication and sustained human labor are sufficient to remove granite, diorite, quartz-rich sandstone and andesite. The model works. It can be demonstrated. It can be observed in laboratory conditions. It aligns with excavated copper tools, abrasive residues, and partially completed artifacts found at archaeological sites. For these reasons, abrasive slurry has become the official explanation and the intellectual anchor for understanding ancient precision stonework. Within its scope, the model performs well. It adequately explains material removal in extremely hard and brittle materials. Quartz, emery, corundum, and other abrasive particles are harder than copper and capable of cutting granite or sandstone when suspended between tool and workpiece. The soft metal tool does not perform the cutting directly, but acts as a carrier, distributing abrasive particles across the contact interface. As rotation or linear motion occurs, abrasive grains fracture and plow microscopic grooves into the stone surface. Spiral striations on drilled cores can be explained by the interaction between rotation, downward feed rate, and the progressive action of abrasive grains. Flat surfaces can be achieved by sustained soaring motions with slurry replenishment. Cavities can be hollowed. Cylindrical cores can be extracted. These outcomes are not hypothetical. They have been reproduced in controlled experiments. The model also explains many of the observable surface features present in archaeological specimens. Under magnification, striations align with expected abrasive motion paths. Spiral grooves on Egyptian granite cores correspond to rotational drilling with downward pressure. Shallow cavities and sawn faces show patterns consistent with abrasive-laden copper tools. The presence of copper implements at sites such as Giza and evidence of abrasive residues embedded in stone further reinforce the plausibility of this explanation. From a strictly mechanistic standpoint, abrasive slurry technology accounts for how ancient artisans could shape hard stone without hardened steel tools. However, adequacy in explaining the fundamentals of material removal does not necessarily equate to completeness in explaining all observed characteristics. The model successfully addresses the question of how stone can be cut. It is less decisive when confronted with the question of how certain artifacts achieved extreme uniformity, internal precision, and mirror-grade finishes across large surfaces and hidden geometries. The distinction is subtle but crucial. Demonstrating that granite can be drilled does not automatically demonstrate that it can be drilled with micron-level concentricity maintained throughout depth. Demonstrating that sandstone can be polished does not automatically demonstrate that sub-micron surface smoothness can be achieved consistently over 12-meter cylindrical columns. In many experimental reconstructions, the results validate the principle while falling short of the archaeological standard. Surfaces may be smooth but not uniformly reflective. Cylindrical cavities may be round but not consistently concentric throughout depth. Mirror-like polish may be approximated, but lacks the homogeneity and absence of visible directional scratches observed on some Ashokan pillars. The experimental outcomes confirm feasibility while simultaneously revealing limitations. The stone can be shaped. The question becomes whether it can be shaped to the observed degree of repeatable perfection using only the reconstructed methods. This is where the conceptual tension emerges. The official model remains dominant because it avoids invoking unknown technologies. Archaeology, by its methodological nature, resists explanations that introduce machinery or techniques unsupported by direct material evidence. The burden of proof lies heavily on any alternative hypothesis. Abrasive slurry requires no speculative leaps. It rests on physics that are well understood. Yet when anomalies persist, features that appear to exceed what experimental replication has consistently achieved, the explanation begins to appear incomplete rather than incorrect. The repeated presence of such anomalies across geographically separated cultures intensifies the issue. Egyptian granite vessels displaying internal symmetry beyond casual expectation, Ashokan pillars with sustained mirror polish, Andean interlocking blocks with tight concealed tolerances, these are not singular curiosities. They appear in multiple contexts, under different cultural frameworks, and in different materials. Each case can be partially explained within the abrasive paradigm. Yet in each case, aspects remain that strain the limits of demonstrated replication. When a pattern of high uniformity recurs, it suggests either that ancient artisans possessed process optimizations not yet fully reconstructed, or that modern replication has not captured critical variables embedded within the ancient workflow. The phrase, "adequacy does not equal completeness," captures the heart of the matter. An explanation can be adequate in principle while incomplete in detail. Abrasive slurry machining adequately explains the possibility of shaping hard stone. It does not necessarily account for every nuance of extreme precision observed in specific artifacts. Completeness would require not only showing that the process works, but demonstrating that it consistently produces the full suite of observed characteristics: mirror-grade homogeneity, deep internal concentricity, systematic abrasion alignment, and large-scale rotational symmetry under realistic labor conditions. One possibility is that missing variables remain unidentified. Abrasive particle grading may have been more sophisticated than assumed. Particle size distribution, hardness variation, and controlled replenishment cycles could significantly influence surface finish quality. Lubricants may have included additives that altered friction characteristics or particle suspension stability. Tool geometries may have incorporated subtle features that improved alignment or reduced chatter. Rotational supports, jigs, or anchoring systems may have stabilized motion in ways not preserved archaeologically. Even small improvements in alignment control or pressure distribution could dramatically enhance uniformity over extended operations. Another possibility is lost process optimization. Knowledge transmitted tacitly through apprenticeship often includes refinements invisible to external observers. The difference between a novice and a master craftsperson lies not merely in effort, but in subtle control of force, timing, and material feedback. Ancient artisans may have developed highly disciplined workflows that minimized variability through standardized sequencing. Pressure application may have been distributed rhythmically. Abrasive slurry may have been refreshed at precise intervals. Surface correction passes may have followed strict geometric patterns. Over generations, incremental refinements could have converged on highly optimized procedures capable of delivering extraordinary consistency without requiring advanced machinery. Yet even with these considerations, some features still appear to demand explanation at a higher resolution. Internal surfaces that maintain uniform curvature despite limited visual access, concealed joints with tight tolerances, and polish that persists with remarkable homogeneity across vast cylindrical expanses imply not only skill, but systemic stability. Stability of process often correlates with mechanical constraint. In modern manufacturing, high repeatability emerges from systems designed to minimize human variability. If ancient systems achieved comparable repeatability, either human control was elevated to exceptional levels through rigorous discipline or physical constraints. Fixtures, guides, rotational supports played a greater role than currently documented. The artifacts themselves therefore seem to demand a higher standard of explanation. They do not contradict abrasive slurry theory outright. Rather, they push it toward refinement. The stone preserves evidence of what was achieved, not merely what was theoretically possible. When the empirical outcome exceeds the average result of modern replication attempts, the appropriate response is not dismissal, but deeper investigation. The burden shifts from proving that stone can be cut to demonstrating how specific levels of precision were maintained repeatedly under ancient conditions. Importantly, acknowledging incompleteness does not require invoking lost advanced technology or speculative machinery. It simply recognizes that our current reconstructions may not fully capture the operational sophistication embedded within ancient practice. The absence of written manuals or surviving workshop diagrams complicates the matter. Tacit knowledge, transmitted orally and embodied in repetitive action, leaves little direct documentation. When social structures collapse, guild systems dissolve, or apprenticeship chains break, such knowledge can vanish while the artifacts endure. The result is a material record without procedural annotation. Thus, the tension between lost knowledge and incomplete explanation remains unresolved. Abrasive slurry technology explains the foundation of stone shaping. It does not conclusively explain every instance of extreme uniformity, mirror-grade polish, or hidden internal precision observed in certain artifacts. The repeated presence of such features suggests that either critical process variables remain unidentified, or that ancient workflows achieved levels of optimization not yet fully reconstructed in experimental archaeology. The stone artifacts themselves stand as silent arbiters. They preserve the final state of processes long vanished. They encode the outcome with uncompromising fidelity. Whether the gap lies in lost refinements, missing mechanical aids, underestimated human discipline, or analytical oversight, the artifacts continue to invite deeper scrutiny. In demanding a higher standard of explanation, they do not refute established models. They challenge them to evolve. Modern material science confronts a challenge that is strikingly similar to the one observed in ancient hard stone artifacts: how to shape materials that are extremely hard, brittle, and resistant to conventional cutting methods without inducing uncontrolled fractures. Quartz-rich sandstone, granite, diorite, advanced ceramics, hardened glass, and technical quartz components all share a fundamental characteristic. They are not ductile. They do not deform plastically in a forgiving way. Instead, they fracture. When subjected to uneven force, they chip. When pressure exceeds critical stress thresholds, they crack catastrophically. The problem is not merely one of hardness, it is one of brittleness combined with internal crystalline structure. In the 20th century, as engineering demands expanded into aerospace, electronics, and advanced ceramics, industry faced the same fundamental obstacle. Conventional cutting methods, rotary drilling, sawing, or milling, proved inadequate for certain materials. Hardened steel tools dulled rapidly. Direct mechanical cutting generated excessive stress concentrations. Even diamond tools, while capable of abrading the surface, could introduce micro-cracking that compromised structural integrity. Engineers required a method capable of removing material in extremely small, controlled increments without triggering fracture propagation. This need led to the development of ultrasonic machining in the mid-20th century. Ultrasonic machining was not designed for aesthetics or symbolic monuments. It was developed for precision manufacturing of brittle, high-performance materials used in critical technological applications. The method addressed the same core dilemma faced by anyone attempting to shape quartz-rich or crystalline stone: how to remove material without destroying the integrity of the remaining structure. The principle behind ultrasonic machining is conceptually elegant. Rather than cutting directly with a hardened tool, the tool serves as an energy transmitter. It vibrates at extremely high frequencies, typically between 20 and 40 kilohertz. These frequencies are far beyond human perception. The tool does not rotate in the conventional sense. Instead, it oscillates longitudinally, moving up and down tens of thousands of times per second with very small amplitude. Between the vibrating tool and the workpiece lies an abrasive slurry. The slurry contains hard abrasive particles suspended in a liquid medium. When the tool vibrates, it transmits high-frequency energy into this slurry. The abrasive grains trapped between the tool and the material surface are accelerated repeatedly. Each vibration cycle causes microscopic impacts. These impacts generate controlled microfractures on the surface of the brittle material. Material removal occurs not through slicing or shearing, but through a process of repeated, finely controlled microfracturing. Each abrasive grain acts as a miniature hammer, striking the surface thousands of times per second. Because the amplitude of vibration is small and the impacts are distributed across countless particles, stress is applied in a highly controlled and localized manner. The result is incremental removal at a microscopic scale. The crucial advantage of ultrasonic machining lies in this incremental precision. Rather than imposing large forces that risk catastrophic cracking, the process removes material in extremely small increments. This allows micron-level control over geometry. Circular holes can be produced with high concentricity. Sharp internal angles can be achieved without inducing large stress rises. Smooth cavities can be formed in quartz, ceramics, and hardened glass, materials that would fracture under traditional mechanical cutting. In modern applications, ultrasonic machining is particularly valuable where traditional cutting fails. Advanced ceramics used in turbine components, glass substrates in electronics, quartz components in scientific instrumentation, and brittle semiconductor materials all benefit from ultrasonic techniques. Conventional drilling may generate cracks radiating outward from the hole. Ultrasonic machining, by contrast, distributes energy across abrasive particles in a way that mitigates large crack formation. This method produces surfaces that are smooth at a microscopic level. Because material removal is distributed and controlled, surface finish can approach extremely fine tolerances. The cavity walls remain relatively free of deep chatter marks. Microfractures are shallow and uniform rather than chaotic. The geometry of the cavity reflects the stability of the vibrating tool and the consistency of slurry interaction. The parallels between ultrasonic machining and ancient abrasive slurry methods are conceptually intriguing, though they are not equivalent. In both cases, the tool does not perform the cutting directly. In both cases, abrasive particles suspended in a medium perform the material removal. In both cases, the challenge is to shape brittle materials without inducing uncontrolled fracture. The difference lies in the source and stability of energy input. In ultrasonic machining, vibration frequency and amplitude are precisely controlled by electromechanical systems. The energy delivered to the slurry is consistent, repeatable, and uniform. The operator does not rely on muscular force alone. Instead, a mechanical oscillator ensures that each abrasive particle impact occurs within predictable parameters. This high-frequency control allows precision that is difficult to achieve with manually applied pressure and rotation. The importance of frequency in ultrasonic machining cannot be overstated. At 20 to 40 kHz, the tool vibrates tens of thousands of times per second. This rapid oscillation prevents large stress concentrations from developing. Instead of one large impact, the material experiences a rapid sequence of small impacts. The fracture propagation remains shallow and contained. The microstructure of the material is gradually abraded rather than violently disrupted. This is particularly effective for materials like quartz, which rank high on the Mohs scale and resist abrasion while being prone to brittle failure. Quartz grains within sandstone or granite behave unpredictably under uneven stress. If struck with excessive force, they can fracture along cleavage planes, producing chips and irregular surfaces. Ultrasonic machining reduces this risk by maintaining energy distribution at a microscale. Another advantage of ultrasonic machining is the ability to maintain geometric fidelity in internal cavities. Because the tool's motion is constrained and vibrational rather than rotationally aggressive, coaxiality and circularity can be preserved with high accuracy. Deep holes can be produced without significant lateral drift. The slurry continuously replenishes abrasive particles, and debris is flushed away, preventing clogging that might otherwise introduce irregularities. Modern industrial processes demonstrate that shaping brittle materials to high precision is possible when energy input is stabilized and microfracture is controlled. This insight reframes the broader discussion about ancient stonework. It shows that the key to precision in brittle materials lies not in brute force, but in energy management and controlled abrasion. Ultrasonic machining is particularly effective in scenarios where traditional cutting fails precisely because it decouples cutting from direct mechanical force. The tool does not gouge the material. It mediates energy transfer into abrasive grains. This distinction is critical. When shaping quartz-rich sandstone or granite, direct tool-to-stone contact can generate high stress concentrations. Mediated abrasive impact distributes stress more evenly and reduces the risk of catastrophic cracking. The surfaces produced by ultrasonic machining often display uniform texture and minimal macro-scale chatter. Under magnification, abrasion patterns appear systematic rather than chaotic. Internal angles can remain sharp because the abrasive impacts are localized and controlled. This capacity to create sharp internal geometries without fracturing adjacent material has made ultrasonic machining indispensable in certain precision industries. It is important to emphasize that the existence of ultrasonic machining does not imply that ancient civilizations possessed high-frequency electromechanical oscillators. There is no archaeological evidence for such devices. However, the modern technique illustrates a principle. When dealing with hard, brittle materials, precision emerges from stability of energy input and controlled microfracturing. The lesson is conceptual rather than technological. In the context of ancient stone artifacts, the question becomes whether some form of highly stabilized abrasive process, whether purely manual, mechanically constrained, or otherwise optimized, achieved a level of energy control that approached the stability modern ultrasonic systems provide electronically. Even if ancient artisans relied solely on slurry-based abrasion, the degree of consistency observed in certain artifacts suggests that their control over pressure, motion, and abrasive distribution may have been more disciplined than commonly assumed. Modern parallels demonstrate that smooth cavities, sharp internal angles, and circular holes in brittle materials are achievable when microfracture is carefully regulated. They show that extreme hardness does not preclude precision. What matters is how force is applied, how abrasive grains interact with the surface, and how stress propagation is managed. Ultrasonic machining stands as a testament to how engineering eventually solved the same fundamental problem faced by anyone attempting to shape quartz, ceramics, or hardened stone. It reveals that the path to micron-level precision in brittle materials does not lie in increasing force, but in refining control. Material is removed in extremely small increments. Energy is distributed rather than concentrated. Geometry emerges from consistency rather than brute strength. In modern industry, ultrasonic machining occupies a niche where traditional cutting methods prove inadequate. Its success underscores a broader truth. Shaping brittle materials requires an understanding of fracture mechanics, stress distribution, and controlled abrasion. These principles, though formally articulated only in recent centuries, are rooted in physical laws that have always governed material behavior. When viewed alongside ancient stone artifacts exhibiting high precision, the existence of ultrasonic machining invites reflection, not as evidence of lost machinery, but as a reminder that controlled abrasive processes can yield extraordinary results when stability is achieved. The parallel lies not in technology, but in principle. Precision in brittle materials demands controlled microfracture, uniform energy distribution, and process stability. Modern science achieved this through high-frequency vibration. Ancient artisans, whatever their exact methods, appear to have achieved outcomes that suggest an advanced empirical grasp of the same underlying realities. When examining certain ancient stone artifacts through the lens of modern material science, a striking pattern emerges. The surfaces, internal geometries, and controlled finishes observed in granite vessels, quartz-rich sandstone pillars, and precisely cut interlocking blocks resemble outcomes that modern engineers typically associate with ultrasonic machining. This resemblance is not superficial. It lies in the character of the surface, the behavior of brittle materials under controlled abrasion, and the preservation of geometry in areas where uncontrolled fracture would normally occur. To understand this analogy properly, it is essential to begin with caution. The comparison does not imply that ultrasonic technology, high-frequency oscillators, or electromechanical systems existed in antiquity. There is no archaeological evidence supporting such a claim. The analogy operates at a conceptual level. It serves as a framework for understanding how precision in brittle materials might be achieved without relying on brute force, uncontrolled impact, or purely improvised technique. The stone remains silent yet precise. It does not tell us which explanation is correct, but it constrains our interpretation. It tells us that whatever method was used achieved consistent outcomes across multiple artifacts. It tells us that internal symmetry was maintained in areas not easily visible during carving. It tells us that pressure was regulated sufficiently to avoid widespread fracture in brittle materials. In some ancient stone vessels, interior surfaces maintain concentric curvature from rim to base. Achieving such geometry requires maintaining coaxial alignment. Without stable referencing systems, deviations would accumulate. The preservation of internal precision suggests either remarkable manual control or supportive mechanical frameworks. Again, the stone preserves the outcome, but not the apparatus. Interlocking architectural blocks in certain megalithic sites fit together with minimal gaps, even on concealed faces. This suggests that precision was not limited to visible surfaces. If fitting were purely aesthetic, concealed surfaces could have been left rough. Yet they were often finished to tight tolerances. This indicates that precision had structural or procedural importance. It indicates that standards were applied consistently, not selectively. Industrial production is defined by repeatability and quality control. Ancient contexts lacked steam engines, electric motors, and mass production lines, yet some artifacts exhibit outcomes associated with industrial discipline. Uniform dimensions, standardized proportions, consistent surface finishes. These features suggest structured workflows. They suggest coordination among workers. They suggest measurement systems and quality criteria. This does not mean that ancient societies possessed factories in the modern sense. It means that process optimization is not exclusive to industrial eras. Human beings are capable of systematic refinement long before mechanization. What the stone demonstrates is that such refinement occurred to a high degree in certain contexts. If modern replication of specific ancient finishes requires industrial abrasives and machine stabilization, the gap between ancient method and modern reproduction becomes a subject of inquiry. It does not automatically imply lost high technology. It does imply that our current reconstructions may be incomplete. Adequacy is not completeness. An explanation that allows material removal is not necessarily sufficient to explain extreme uniformity and polish. The unresolved question remains: was this knowledge the result of artisanal genius refined across generations, or does it reflect a technological tradition that has been partially obscured by time? It may be a false dichotomy. Artisanal genius and technological tradition are not mutually exclusive. A tradition can institutionalize genius. Genius can elevate tradition. The presence of structured outcomes suggests that individual skill was supported by shared methods. Stone, as an archive, does not dramatize its message. It does not exaggerate its achievement. It simply preserves geometry, surface finish, fracture behavior, and alignment. It preserves evidence that ancient artisans understood how to manage friction, distribute pressure, and sequence operations. It preserves evidence that measurement and symmetry mattered. It preserves evidence that certain standards were met repeatedly. Across millennia, weather erodes edges and dulls gloss, yet the underlying precision persists. Cylindrical shafts remain cylindrical. Symmetrical vessels remain symmetrical. Interlocking joints remain tight. These enduring qualities reflect engineering insight embedded in mineral structure. When we study ancient stonework carefully, we are not merely studying the past, we are studying preserved process control. We are reading a technical archive written in abrasion patterns and curvature lines. We are interpreting a language of pressure and motion that requires no alphabet. Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.